In this tutorial, we will be discussing the molecular orbital theory. In previous tutorials, we have been discussing valence bond theory, which uses VSEPR, valence shell electron pair repulsion, and hybridization of atomic orbitals to explain bond formation. It predicts only the type of hybridization, not which molecules will hybridize. It can also only explain bonding with compounds bringing an even number of valence electrons. Molecular orbitals, however, indicate that when elements bond, a bonding orbital forms. It can explain both even and odd valence electron compounds, and it correctly predicts bonding strength as well as magnetic properties of compounds. Finally, it predicts whether a molecule or ion exists altogether. Molecular orbital theory makes the assumption that when two elements form a bond, a new molecular orbital bonding entity is formed, not the mixing of atomic orbitals, which is what valence bond hybridization states. Electrons entering the molecular orbital follow the Pauli exclusion principle, indicating that the electrons enter the lowest energy first. It also follows the Hund's rule, which states that the electrons will be at parallel spin going in opposite directions. Valence electrons in the molecular orbital theory are delocalized, unlike the valence bond theory. These electrons are not located specifically above or below the plane of the bond. Valence electrons are in orbitals, called molecular orbitals, spread over the entire molecule. The basis for molecular orbital theory comes from quantum mechanics. Now, this is a new concept for you at this point. Molecular orbital theory uses bonding orbitals called bonding and anti-bonding. With bonding molecular orbitals, they are stabilizing. They're lower in energy than the atomic orbitals. Anti-bonding, however, are destabilizing. They're higher in energy than atomic orbitals. The electron density is located outside the internuclear axis, meaning not between the two nuclei that are being bonded together. The orbitals are considered to be out of phase. If you remember, electrons behave as both particles and as light. So if we're looking at it as light, they're out of phase with one another, whereas bonding are in phase. Electrons in anti-bonding orbitals cancel stability gained by the electrons in the bonding orbitals. So let's take a closer look. When the wave function combine constructively, so this is when the electrons are in phase with one another, the resulting molecular orbital has less energy than the original atomic orbital and is called the bonding molecular orbital. Notice that they're coming together here. This is the sigma or the pi. And this right here is an example of the sigma 1s bonding orbital. Most of the electron density is between the nuclei in the bonding orbital. With anti-bonding, when the wave function combined destructively, so here we have destructive interference, the resulting molecular orbital has more energy than the original atomic orbitals and is called the anti-bonding molecular orbital. Notice that there is a node between them. There's an empty space, and they're not on the same phase. Also notice that they're called sigma star, pi star. That's to help show that it's not bonding, that it is actually anti-bonding. Most of the electron density is outside of the nuclei, outside between the nuclei. And there's a node between them. So let's take a look at the molecular orbital theory. The number of molecular orbitals formed is equal to the number of atomic orbitals used. What this means is if we take hydrogen, for example, actually this is helium. Helium is 1s2. So we have an s orbital here, and if we have two helium atoms coming together, we have another s orbital over here, for a total of 2 orbitals. That's why we have a bonding and an anti-bonding. For every orbital, there's a molecular orbital. Bonding molecular orbitals have lower energies than the atomic orbitals. Notice that it goes down for the bonding orbital. Anti-bonding, or the star molecular orbital is higher in energy, and that's when it's out of phase. The 2 electrons exist per molecular orbital. So we had 2 on the left and 2 on the right. They come together to have 4. So we have 2 on the bottom and 2 on the top. Electrons enter the lowest energy molecular orbital and upward. So we start at the bottom and work our way up. So as another example, we have 1s here. We have 1s here. They're coming together. Notice that they lower in energy to form that bonding orbital in phase. For p orbitals, px for example, they come together and they have this bonding lobe. However, if they're out of phase, notice that the different colors, there's a node that forms between them. Kind of like if you try to push around magnets. Once again, atomic orbitals, when they're in phase, they're bonding. When they're out of phase, they're anti-bonding. Let's talk about bonding order, because that determines the strength. The bond order is all about strength. The greater the value, the stronger and the shorter the bonds between the atoms will be. It's determined by taking the difference between the number of electrons in bonding and anti-bonding orbitals. So it's the bonding electrons minus the anti-bonding electrons divided by 2. You only need to consider the valence electrons in this process, and it can be a fraction. A bond order with a value of 0 indicates an unstable species, less stable than the individual atoms themselves, so therefore they're not going to bond. So does helium exist as a molecule? We know from our experiences that helium is a noble gas, and noble gases typically don't react readily. At least not as readily as the other atoms on the periodic table. So let's see in theory if it's supposed to exist. We know that helium has an electron configuration of 1s2. So here's 1s2 right there. And here's for the other atom. So that's a total of 4 electrons. So here's 2, and then up here is 4. So the bonding is 2 on the bottom, anti-bonding minus 2 from the top, divided by 2. That is equal to 0. The 0 bond order indicates that helium, He2, does not exist as a molecule. Let's try another one. Let's try boron. Boron has the electron configuration of 1s2, 2s2, 2p1. It brings in 3 valence electrons, and that's what we're going to focus on. So if we have a boron on this side and a boron on this side, 1s2, 2s2, 2p1, 2s2, 2p1. That I got from the electron configuration. Valence electrons enter the molecular orbitals from the lowest energy upward. So these are going to combine to fill the middle ones. So here's our sigma, and here's our sigma star. We had 2 4 electrons, 2 4 electrons in the middle. Now we have 1 on each side. You fill them up individually first, and then you go back and fill it up. So the bonding order here, we have 2 sigmas here, 2 pi ones here. So 4 total for bonding, minus 2 for sigma star here. We don't have any star ones up here. Divided by 2. That equals 1. So our bonding order is 1. And so that's a fairly strong bond. Now look here. Notice you have single electrons here. That actually affects the magnetism. Bonding theories and magnetism. Lewis theory, as well as valence bond theory, do not predict the molecule's magnetic properties. Molecular orbital theory can predict the magnetic properties. Magnetism results when unpaired electrons occur, like the boron we just saw. Materials that exhibit magnetic properties are referred to as paramagnetic. Paramagnetic have unpaired electrons. So the unpaired electrons have magnetic properties. Materials that do not exhibit magnetic properties are known as diamagnetic, and they have all paired electrons. Oxygen is another example of a paramagnetic compound. So if we look at the molecular orbital of oxygen, we know that oxygen is 1s2, 2s2, 2p4. So here's 2s2, here's 2p, we have 1, 2, 3, 4 electrons in there. We have the same on this side. So 2 sigma star, because we have 4 total. Now we have 4 electrons here and 4 here for a total of 8 electrons. So 2, 3, 4, 5, 6, because you do it one at a time, 7, 8. Notice the unpaired electrons here, because we spread them out before we pair them up. The fact that they're single means it's paramagnetic, which means oxygen is actually magnetic. Let's figure out the bonding order just for practices. The bonding electrons, so we have 2, 4, 6, 8 bonding electrons minus 2, 3, 4 anti-bonding, all over 2. So that equals 4 over 2, which it has a bonding order of 2. Notice that when we make the Lewis dot structure, it has a double bond. That's what that bonding order means. Now there is one thing that we want to note. Let's take a look at the row, the second row from left to right. So boron, carbon, nitrogen, and then oxygen, fluorine, and neon are all in the same row. They're all in the second energy row. Look here at the order in which things are made. So sigma star are the same, but then for the smaller atoms, actually for the lower atomic number, I should say, not necessarily smaller, for the lower atomic number, pi, sigma, pi star, sigma star, whereas here is the sigma, pi star, sigma star. Notice that things have been flip-flopped. These two have switched places. And that's because of the S and P interactions within the atomic orbitals. This is called the mixing of the sp orbitals. And this happens after element 7. So after element 7, you're going to have this arrangement. But before element 7, you'll have the pi sigma. These two will be flip-flopped. So let's take a quick review of valence bond theory versus molecular orbital theory. The valence bond theory uses VSEPR, valence shell electron pair repulsion, and hybridization of atomic orbitals to explain bond formation, and can only predict the type of hybridization, not which molecules will hybridize. It can only explain the bonding with compounds bringing an even number of valence electrons. Molecular orbital theory is much more robust. It forms elements bonding orbital forms. We have bonding and we have anti-bonding, which is signified with a star. Bonding is in phase, anti-bonding is out of phase. It can explain both even and odd valence electron compounds. It correctly predicts the bond strength using the bond order and the magnetic properties of the compounds. If it's paramagnetic, it's unpaired electrons in those orbitals. Diamagnetic means that all the orbitals are all paired up. And it correctly predicts whether the molecular ion exists, referring once again back to that bond order. And I hope that gives you an overview of the molecular orbital theory.